All right, let's jump right in. What we're looking at here is a manufacturing blueprint for something called QCPAN. And this isn't just another piece of network tech. No, this is a blueprint for something fundamentally different. A network that's designed to act less like a machine and a whole lot more like a living organism.
And this right here, this is the core idea, and it'll kind of blow your mind. The system isn't programmed to communicate. Instead, the entire goal is to get all the parts into a state of perfect collective rhythm. And out of that shared state, communication just happens. It emerges. The network literally learns to talk all on its own.
So how in the world does it do that? Well, the magic ingredient is a concept called phase coherence. Imagine you're at a huge concert. At first, everyone's clapping is just a wall of noise, right? But then, slowly, without anyone telling them to, people start to sync up. And soon you've got thousands of people clapping in one single powerful unified beat. That is phase coherence. And it's the absolute bedrock of this entire system.
So here's how we're going to break it down. We're going to build this digital organism piece by piece. We'll start with its incredibly stable heartbeat, then we'll look at its unique sensory skin, we'll connect it all with a nervous system, and finally, we'll give it an adaptive brain.
Okay, layer 1, the phase resonance core. Now, don't just think of this as a timer or a clock. It's so much more than that. This is the network's pacemaker. It's the source of that fundamental, unwavering rhythm that everything else is going to lock onto.
The blueprint is incredibly specific about how stable this heartbeat has to be. The spec is for an Allen deviation of less than 10 to the minus 11ths. Now, I know, a number like that doesn't really mean much on its own.
Until you put it in perspective. Get this. That's a rhythm so precise, it's like having a clock that would only drift by a single second over 3,000 years. And this level of stability, it isn't just a nice-to-have feature. It's the absolute, non-negotiable foundation that this whole living network is built on.
So what happens if that perfect rhythm gets totally knocked off course? Well, built right into the core is a memory module. It uses this special battery-backed RAM to constantly save the network's last known good state. This is basically the system's long-term memory, which lets it remember what stability felt like and lets it recover really fast from a total system collapse.
All right, on to the next layer. Let's see how this thing actually senses the world around it. This is the orbital radiation surface, and you can think of it as the organism's specialized skin, or its primary sensory organ.
The blueprint uses this incredible phrase, orbital field containment. I mean, it sounds like something straight out of science fiction, right? But what it means is that this surface isn't just a passive antenna. It's actively engineered to create and hold stable electromagnetic fields around itself. They're like these invisible containers for energy.
And the way it's built is just fascinating. The skin is made from a special material that has extremely low signal loss, but the pattern etched onto it, that's the key. It's a complex fractal known as a Minkowski island. This weird shape lets it resonate on multiple different frequencies at the same time, kind of like how an atom can hold electrons in different energy orbitals. And the wildest part? It's also designed to be elastic, so it can bend and vibrate and take a beating without breaking.
And you can bet that this multi-mode capability is tested like crazy. At low frequencies, it's got to act like a stable, all-around sensor. Then, in the mid-range, it has to be able to form a focused, directional beam. And at the highest frequencies, it needs to be able to sync up using all the chaotic reflected signals bouncing around a room. It's a truly versatile sensory organ.
So we have a heartbeat, and we have a skin, but now we need to connect everything. We need a nervous system. That brings us to layer 3, the phase bonding network. This is the very fabric that weaves all the individual nodes together into one coherent, unified organism.
And what's cool is that this nervous system isn't a one-size-fits-all deal. It can be set up in different ways for different jobs. For a dense space, like an office building, you'd use a simple, predictable geometric mesh. To connect a bunch of buildings across a campus, you'd use what's called a small world network, which has a few key long-distance links. And to build a whole citywide backbone, you create a scale-free network, built around critical, super-connected hubs. And that brings us to the final piece of the puzzle, the brain. This is layer 4. The Adaptive Hybridization Controller, or AHC. And here's the amazing part. Every single node in the entire network gets one. This is an essential command center. It's a completely distributed intelligence.
So, what is this tiny brain doing all day? Well, its most important job happens really, really fast. We're talking 100 times per second. That's right, 100 times, every single second, the AHC checks what the blueprint calls the master stability law. You can think of it as the fundamental equation that proves the entire system is healthy and in sync. It's like a constant, super fast check of the organism's vital signs. Now, all of this obsessive monitoring is for a very good reason. Because this system, for all its cleverness, faces one primary existential threat. The question is, what is that single greatest danger? The blueprint's own risk analysis identifies it loud and clear. It's called a phase catastrophe. This is the nightmare scenario. It's the moment when random noise from the environment just completely overwhelms the system's ability to stay in sync. That beautiful, unified rhythm dissolves into chaos, and the whole network just falls apart.
But here is the truly brilliant part. The system is designed to survive this. The instant the AHC detects a collapse, it triggers an emergency auto-recovery. It's like a built-in survival instinct. It immediately switches to a backup oscillator, and then it pulls that phase seed, that last known good state from its memory, and injects it back into the system to kickstart the whole synchronization process all over again. It can actually heal itself.
So when you put all these pieces back together, the heart, the skin, the nerves, and the brain, it's really important to realize that what you have is so much more than just a collection of hardware.
We've just assembled a system that has a stable heartbeat, a fractal sensory skin, an adaptive nervous system, and a distributed computational brain in every one of its cells. This QCPAN document, it isn't just a blueprint for a network. It's a blueprint for a network that lives. And that leaves us with one final fascinating question to think about. If creating the perfect conditions for synchronization allows a complex behavior like communication to simply emerge without ever being programmed, what else could emerge? What other complex behaviors might we discover, just waiting, in systems that we design not as machines, but as organisms that are truly, collectively alive?